Okay, can you see my screen?
Yes, sir.
All right. We are on the verge of finishing the course. Tomorrow would be our last lecture. And as you know that we were discussing pipelining, we introduced basic concepts and some important results. So today we will continue on that and discuss some of the, in more detail, some of the approaches which are deployed to manage the different kinds of hazards that might appear in pipelining. Well, so you remember the last week we were talking about pipelining. So what was our main observation or the main results you have learned so far? What would be the maximum speed up?
So the number of pipeline stages.
Right. So that's one important result. Another important result is that once the pipeline is full, so then in the ideal case, what do we expect? In every clock cycle, what do we expect?
All stages to be full.
All stages full, and then once it is full, then for every clock cycle, one instruction will be finished, right?
Yes, sir.
It will finish. That means it will finish completing one instruction at every clock cycle if everything is ideal. And we also noted that the latency. I mean the difference between the finishing points, the two consecutive finishing points, is determined by the longest stage of the pipe. And it can be easily shown that if the pipeline stages are balanced, that means if all stages are equal in time, so then the speed up is maximized. Okay, so these are the ideal cases, but we have noticed that there are many obstructions or hindrances which are called hazards. And the presence of hazards is almost inevitable. I mean, you cannot avoid that. And we classified different kinds of hazard. You remember some of them?
So structural hazards and control hazards.
Yes, structural hazards. What was that? Due to what? It is in the conflict of in the available resources. That's what is structural hazard. That means the resource is busy. Control hazards, you said. What does it mean? That you have some branch instructions, and suppose there is another instruction which follows the branch, which normally enters the pipeline, but that successor instruction may or may not be executed. It depends on the decision taken by the branch instruction, right? And the decision may be still awaited because the next instruction enters into the pipeline just after one clock cycle. And the decision regarding the control or the branch, whether suppose you have branch equal or so, so that equality comparison is done in the execute stage, in the later in the pipeline of the previous instruction. So you don't know whether you don't know the outcome of the branch instruction which is being currently executed, and therefore the next instruction may or may not be executed, depending on the target address. So that's what is called control hazard. We will discuss about that today. What else? There is another kind of hazard. Structural control, and the third one?
The data hazard.
Data hazard, right. So you are waiting for something. You are waiting to read something which is not yet available. You are waiting to read the content of some register, but that register may is still being updated by previous instructions. Maybe an add instructions or load instruction, whatever. Well, so these are the three basic classes of hazards. So hazard is a situation that prevent executing the successor instructions in their intended cycles. So each successor instruction is supposed to be executed one after another, but because of the hazard created by the previous instructions or the instructions which are already in the pipeline, it slows down the flow. And as we have just mentioned, that we have three kinds of hazard. Structural hazards mean the required resource is busy. Data hazard means you are waiting for something, but it is yet to be completed. So you need to wait for previous instruction to finish some data read or write. And control hazard, So you have some branch instruction, and the choice of the next instruction depends on the previous decision, the decision of the branch instruction, which is awaited. Well, recall this example once again. Notice that. Okay, so this means this is the clock cycles. The time sequences are shown horizontally, and this is this matrix is known as the pipeline diagram. So the instructions are written here along in the column, and the 5 stages of the pipeline are shown here. So what do you notice here? You have an add instruction, and which sorry, I made a mistake here. Yeah, this should be R1, R2 plus R3, something like that. Okay. So you have an add instruction here, and which is supposed to update this register, And in the next instruction, you are reading this register. Okay, so this is the destination register of the add instruction, and this is the source register of the subsequent instruction. Similarly, this is the source register of the following instruction, and this is the source register of the following instruction. So in the traditional pipeline, suppose we don't have any extra hardware. Okay, then in what time cycle this register is being updated? Will be updated. This add instruction.
5th clock cycle.
5th clock cycle, right? Yes. In the 5th clock cycle, this will be updated. And we also note that we have a register read-write strategy. That means the writing would be done in the first half cycle and the reading would be done in the second half cycle. And that way we can resolve some of the hazards. So it would be, if nothing is in the traditional pipeline, this will be updated in the 5th clock cycle. But you are requiring it in the 3rd clock cycle, where you are going to read the source register here, right? And the subtraction operation would be executed in the 4th clock cycle. So therefore, as you can see that I'm going to read the content of this R1 in clock cycle 3, whereas it is available in clock cycle 5. Clearly, this data is not available. So therefore, if I don't do anything, I have to stall it so that, I have to wait until the 5th clock cycle until this data is available, and I can resolve the stall. I can resolve the hazard that way. So this is a kind of data hazard which we discussed, but we also notice that this addition is being performed in this execute stage, and the result is saved in this interface register here, because as we know that in the pipeline implementation, between 2 consecutive stages, we need to keep some interface registers or interface latches. So at the end of the 3rd clock cycle, the current value of R1 is already stored in this interface latches. Whereas in order to execute the subtract instruction, I need it before the execute stage here. So therefore, it is already in the system. The data is already available before I need, but the required hardware is not there. So if I add some required hardware so as to transfer the data which is stored here and make it available to the input of this execute stage, so then the subtraction instruction can be executed without any stall. And this is what is called forwarding, right? And you also note that the same source register is being asked for here and also here. Okay. So since the result is available at the end of the execute stage by adding some appropriate hardware, which is called the forwarding hardware, I can resolve this. I can execute the subtract instruction, which is already entered into the pipeline without any stall. Is this okay for you? I mean, I think we discussed this earlier. Any doubt or question here?
Sir, how is a stall actually like achieved in hardware? Like how is it stored?
Yes, very good question. First of all, so this is we are looking into the diagram where and we can see what is happening. But here you are right. How it is being it is being implemented in hardware. First of all, you need to identify whether or not the hazard has occurred. And that's why we need in the forwarding hardware we have many components. One of the component is the hardware module that enables the transfer of this information to here. That's one component. The other component is you need to identify whether or not this hazard has occurred. So how do I identify that? One way of identifying is this: if you look into the sequence, and so if the destination register matches with the source register consecutive instructions or the successor instructions, so then you can see the possibility there is a hazard, right? So the forwarding hardware actually checks that. And once it is done, it stalls means, it just stops flowing the copying of that information from the one stage to the another stage. So we'll discuss it briefly later on because we don't have much time for talking about those hardware details. But we'll, in principle, how it is done, we'll discuss in tomorrow's lecture. All right.
Thank you, sir.
Okay. Now, my next question is, I will look into this third instruction, and here again you have this register R1, which is the source. Okay. And execution is being requested here. So the value of R1 is already available in the interface register, but where? From where I need to transfer this now? For the subtract instruction, it is okay. It is being transported from this interface latch to the input of this here. For this one, is the same value, is the same register. But where it is now? My question is whether it is in this interface latch here or in this interface latch now.
So in the latter one.
Is the latter one correct? Because as we move into the pipeline, everything, the content of this latches will be copied into the next set of latches. So therefore, to execute this one, correct, you need to enable a data transfer from this interface latch to the input of the execute. Okay. Now for this one, we don't have any problem because in the same cycle, in the second half of the same cycle, that data is available. So what do we learn from this example? That if I have, so this is one R-type instruction and this is another R-type instruction and so on. So everything is R-type instruction. So if appropriate hardware, forwarding hardware, data and the hazard detection hardware is available, and appropriate means the transfer mechanism from the execute to execute, from memory to execute. So then everything can be executed here without any stall. Isn't so? So with forwarding mechanisms such as execute to execute and memory to execute, all data hazard in this case can be eliminated. And the total number of clock cycles you need to finish this 4 instruction would be 8, because we don't need to stall this one. Okay. Now let us in the previous case, see, you have this is the destination and all our sources here. Okay. Now look into this example now. Again, you have this 3 add instruction in sequence, and here notice that register 1 is the destination register, and here it is the source register. Again, for this one, the same register is the destination register of the previous one. So if you look into if you draw the pipeline diagram, what we will see? There is a hazard here and there is hazard, 2 consecutive hazards involving the same register. Okay, so I leave it to analyze that how to handle this hazard. What kind of, I mean, you have assumed that you have forwarding mechanism, but just draw the pipeline diagram and you see that how to manage these transfers. You understand the problem, right?
Yes, sir.
Yes, so you have multiple destinations. In the previous example, you have one destination and multiple sources. Here you have multiple destination, multiple sources involving the same register. And that's why it's a little complicated. Anyway, so I leave it to you to study this example. Okay. So this is called load use data hazard, because so there is a load instruction and the load instruction updates a destination register R1, and that destination register is asked as a source register here in the subsequent instructions. And this is called load use data hazard or load data hazards and so on. So what is the difference? Suppose instead of load, I have an add instruction as before. So do you see any difference here? I mean, which one is more difficult? I mean, if I have add instruction here and in this example you have load instruction here. Which hazard is is more disturbing?
Sir, the second one.
Second one, because
The data comes after the 4th stage.
Right. You just got the point. In the previous example, data was available at the end of the 3rd clock cycle. Here it is available at the end of the 4th clock cycle. So therefore, the difference between, the time at which it is available and the time at which it is being asked for, that reduces. Therefore, this hazard is more dangerous. So here it is available at the end of this 4th clock cycle because memory has to be accessed. We may not wait until it is written to the registers, but you have to wait until at the end of the 4th clock cycle it would be available here. And you are needing it and you require it here. I mean, if there is no, if everything is ideal, you are requiring at the beginning of the execute stage. Whereas it is available at the end of the memory stage of the previous one. So you have a situation like this, right? I mean, if you don't have anything, ideally this data would be available here and you want to read it here. Even if you have forwarding hardware and so, even then it is available here, but you require here in backward time. That is not possible because the data would be available in the future. So in this case, so when something, and if the source register immediately follows a load instruction with the same destination register, then no forwarding hardware would solve this problem because this is backward in time. So therefore, what do you need to do?
To stall for one cycle.
Yeah, you stall for one cycle, and that is inevitable. Now, once you stall, then the requirement of this register and the other one, those will be solved automatically. Because see, once you stall, then this execute stage just crosses this fourth cycle. So therefore, now the forwarding can be done. You still need forwarding from the memory output from this interface to the input of the execute stage. Well, and for AND instruction or instruction, that would be resolved automatically, because you need the same value farther away, further down the pipeline. So you need at least one clock cycle here. So one stall cycle is needed, and also you need this forwarding from memory to execute. Okay. The next one can be resolved, using just this half cycle rule. And for the last one, nothing. It is clearly available because it is already written into the register file, so it can read it comfortably. Okay, so you need forwarding hardware. At the same time, you need to give one stall, and therefore this program would finish the 9th clock cycle. So the total number of clock cycles to run this code is 9, and whenever you can see that if a register is immediately needed following a load, then stall is inevitable. When the destination of load is the source of the next instruction, then you have to insert stall anyway. Okay. So therefore, if we look into this hardware layout, so these are the interface latches between ID and execute. This is between X and mem, between mem and write back. And these are the muxes which control the inputs to the ALU. And so therefore we need this forwarding data paths from the output from this interface latches to the input to the mux, so that this data can be forwarded to the input of the ALU, and similarly from the memory stage, to this mux as well as to this second input. Because so in an add or subtract instruction, you need two source registers. So so that's why the forwarding should be done to the both muxes. And you also need this additional hardware that we just talked about, that how to recognize the forward hazard and how to enable this stall. Once you recognize the presence of the hazard, this forwarding unit will send appropriate control signal to control this mux lines, the multiplexer inputs, so that this data path is activated. Well, now regarding data hazard, can you do something more? So we have this forwarding, stall, and addition of forwarding hardware, and then use stall if it is inevitable, and so on. So let us look into this example. This is the MIPS code for this C program, A equal to B plus E and C equal to B plus F. Well, so here, notice that there are a couple of things just in the light of the previous discussion that we had just now. So you have a load instruction here, and this is the destination register, and that destination register is immediately asked as a source register of the successor add instruction. And similarly, if we look into this load, we have the destination register T4, and in the next instruction add, so this is the same source register. Also, there will be hazard here, because the T1 is also asked here, but can that be managed by forwarding? Okay, first let us look into this load instruction and this add instruction. So we have a destination here, source here, right? Okay, so this load instruction is here and this add instruction is here. And in between we have another load instruction, so we will consider that later on. So what would be the pipeline diagram of this first instruction and the third instruction? So we have these 5 stages, and since this is the third instruction, this will be shifted by 2 clock cycles. So will there be hazard between the first and the third? Between these two? We just discussed that. At what time T1 would be known?
After 4 clock cycles.
And here you need here, right?
Yes, sir.
So you need forwarding anyway, right? Forwarding hardware you need, then you can resolve this. Otherwise, you have to use stall. Assume that you have forwarding hardware. Okay, so we can resolve this. But how about this? Can you resolve this? So this is T2 here and T2 here, and similarly you have T4 here and T4 here. So, but whatever we have studied so far, you need one stall is inevitable here and another stall is also essential here, right? So how many clock cycles do you need, even in the presence of this forwarding? First one would take 5 clock cycles, then 6, 7, 8, 9, 10, 11, and 2 stalls, right? Okay. Do you agree with me or not?
Yes, sir.
2 stalls inevitable even with forwarding, total 13 cycles. Now let me ask you one question. Is there any way you can further improve it?
Sir, we can. Oh no, what? Reordering will probably not help here.
No, say it again. Rewarding would help. You are on the right track.
Okay, yes, we can push the add and the first add and store W after the first load, after the third load word.
Yes. Some reordering you can do so that the gap between the load and the next and its next use increases, isn't so? Because if the load, see, look into the first and third. So it means what? Although the same register is needed, T1 here and T1 here. But if there is a gap of one instruction, then we can manage by hardware, right? The only problem arises when there is an immediate use of load. They are consecutive. So if I can rearrange the code in such a way so that in between load and add there is something else, and similarly in between this load and add there comes something else without violating the semantics of the program, then possibly we can avoid these 2 stalls, isn't so?
We can shift the last load above.
Sure, you can shift this last load here.
Yeah.
Before add.
Yeah.
Correct. Just do that, And you are done then. How many clock cycles we need then?
11.
Right, correct. So you have already understood the trick, right? So no stall. You need forwarding hardware, but you can just finish exactly within 11 clock cycle without inserting any stall. So this is a great idea, isn't so? But who would take this decision then? And at what time? Indeed, this is a nice idea, but who would take this shuffling, this code shuffling? And you have to understand that there is no change in the semantics. So it needs the analysis of data flow graph, right?
Probably the compiler will do it.
Right. In the stage, the compiler can do that. But now you can since you are studying compiler at the same time concurrently in this semester. So now you see that if the target machine is architecture supports pipelining, then the job of compiler would become much more complex. Because when you study the compilation techniques, we normally don't care about whether or not the target there will be pipelining or other kinds of advanced architectural features present. So you need to do a data flow analysis to figure out whether the shuffling of code is possible. The main idea is to create distance between this load instruction and its subsequent use. So compiler can do that, but it has to be, if you have a smart compiler which can look into this subtleties, possibly it can do that. Because otherwise in the runtime it would be too much, it will be too difficult because the instructions will enter into the pipeline one after another. And then who is going to determine this? There will be a lot of pressure on the hardware circuitry in order to identify these kinds of hazard and then reshuffling them. That would be too much. You have to do it in advance during the compile time. So in summary, so you have if you have data hazard, either you add some kind of forwarding techniques so that some of the hazards can be resolved. And you have the software techniques also by reshuffling the code. Because the main reason behind the occurrence of a hazard is nothing but the timing management. What data is available when. And therefore the shuffling of code and is also important. Okay. Reorder code to avoid the use of load result in the next instruction. That was the main idea. And if there are examples where you can still reshuffle it without changing the meaning of the program, then it could be done, provided you have a smart compiler. Okay, so let us now classify these hazards. I think we talked about this. So far, we are talking about the read after write hazard. That means you have a destination here and you have a source at the subsequent instructions. So I'm going to read this, but the writing of the previous instruction is not yet completed, right? So that's why it's called read after write. Write is still awaited, but I am at the moment, but I am on the verge of reading it. So instruction J tries to read the operand before the previous instruction updates it. So that's what we discussed so far, and this is, as you can see, this is the caused by the dependence. Data here, data is dependent on the previous one. So this is called read after write, raw. You might have other kinds of hazards also, write after write. So this is something, you know, so you are writing the same register by two consecutive instructions or something like that, you know, like this. Okay, so you have load, and this is the destination register here. So one would be register 1 is being updated by instruction I. And in the next instruction, it is again being updated by the subtract instruction. You know. Okay. So let us forget about the semantics of this program. You might say, well, it is being updated here, then what is the use of this load instruction? Let's forget about that. Suppose you have this kind of thing. But now, it might happen that so final updation which is should be made by instruction J. But is it possible that this has been updated by instruction J, and after that, I is updating this? Is that possible? I mean, it is being updated in an incorrect order. You know. If so, then we will say this write after write hazard. You know. If the update is being done in incorrect order, you know. I mean, this is being updated first and then it is being updated for some reason. Is it possible? Hmm? What do you think?
Sir, in this case, the first instruction is redundant, right?
Yes, that's why I told you it is redundant. But
if the I8 instruction was stalled by another instruction, then in that case the one will be updated after J instruction.
Okay, let me tell you another thing. Yeah, that's one possibility. The other possibility is, you know, so you have load instruction, you have memory access, right? Suppose there is a cache miss and so on, you know, page fault, etc., etc. And the next instruction has already entered into the pipeline, and there is no apparently data hazard because it is using something else. Okay. So instruction I is a memory access, and suppose there are cache misses, so you have to wait for few clock cycles. After that, it is available and it is updated here. You know, the next instruction in the meantime has entered into the pipeline. You know, and maybe if you know, I mean, if it is allowed to continue in the pipeline, then it will update here. You know, and it will update later, creating a hazard. You know. Right? So I'm just showing you a possibility, you know, this might happen. You know. One way to avoid this, you know, what we do, so these are stall cycles. So when you insert stall cycle, you stall, I mean, during that interval, let us stop all the instructions. You know. I mean, here what you see that one instruction is being stalled, but the next instruction is allowed to proceed. Don't allow that. If it is stalled, let us stall all the instructions. I mean, like this in the previous example. See, when you insert a stall, it is it? Yes. So when you insert a stall, that stall affects all of them. You know. Everything is pushed. So this is the normally this is easier to implement. You know, but if some other pipeline implementation, if it is allowed to enter and proceed, then this kind of hazard might occur. You know. Just showing you the example, we will not discuss much on that. So there is a possibility, you know, and this is called write after write hazard. So writing is be performed in the wrong order. There are similarly, so you have read and write. So there are 4 possibilities. And another possibility is write after read. Question is, can J write the register earlier before it reads? See, in the previous instruction, this will be read, and in the next instruction, it will be written. However, if this instruction is delayed and somehow this instruction is executed earlier, then it will be written earlier, before it is read. So this is write after read. However, in MIPS, this kind of MIPS pipeline, this kind of hazard will not occur because the reads are early and writes are late. So here it cannot occur, but in other machine architecture, there is this kind of hazard might occur. Anyway, so we have just 4 classes and also read after read. This is not a hazard. So these are different classification, but we are mostly concerned with the first one, the read after write, a raw hazard. And we talked about several techniques of forwarding and code reshuffling and half cycle strategy of reading and writing registers and so on to manage those kinds of hazards. So that's the latest summary of our load use hazard and so on. It is not possible to avoid stall by forwarding, not always. If the load is if the load destination is immediately used, and if there is no way we can reshuffle it and so, then the stall is inevitable. Because the value is not computed yet when it is needed. It is backward in time. But once you insert a stall, then forwarding hardware would take care of the rest of the cases. That's all about our data hazard. And now we'll move on to discussing. Okay, first of all, let us first define what control hazard is. So in our MIPS pipeline, we have assumed that we have implemented BEQ, branch equal instruction. And there are instructions following branch. So here the problem is that the destination address, the outcome of the branch is not yet known. But at the same time, the next instruction which physically follows the branch, that means at the next sequential instruction, PC +4, that has entered into the pipeline. And that particular instruction may or may not be executed. It depends on the outcome of the branch. So if the target is taken, if the branch is taken, then the next instruction has to be flushed out. If the branch is not taken, then the pipeline will flow normally. Isn't so? Also, there is another case. Suppose you have instructions like this, add T1, T2, T3, and suppose after the addition, after addition operation, there an overflow occurs. And in the case of overflow, sometimes there is an exception is invoked, and the control may be transferred to some exception handling routine. So this is also a kind of hazard, because usually you want to perform the next instruction already enters the pipeline. So instead of executing that, you have to execute the exception handling routine. So this is another possible cause of control hazard. Well, so branch determines the flow of control, and fetching next instruction depends on the outcome of branch. So let us see that how you can avoid this kind of instruction and this kind of hazard, and what penalty do you have to make? Is there any hardware kind of solution, hardware based solution, or if we don't have any additional hardware, then what else we can do? Just like in the previous example, in the previous classes of hazard, like data hazards, we did addition of like forwarding and so on. So in case of control hazard, what kind of actions or what kind of things you can do? Okay, so let us look into this branch EQ instruction. So you are comparing the outcome of two registers, right, in branch EQ. So at what instant of time this would be known? There are two things. One is the computation of the outcome, and then the program counter has to be updated accordingly. The PC update hardware is needed. Whether the content of the PC would be PC plus 4 if the branch is not taken, or PC plus 4 plus the target offset if the branch is taken. So if you remember this overall implementation of the processor, so there are specific hardware that takes care of this PC update operation. So when do you think this branch outcome would be known to you? Assume that the following instruction is the load instruction. So if the branch is not taken, then the load will be executed. If the branch is taken, then something else would be executed. When the outcome of the branch instruction would be known to you, known to the system. When does PC is updated? You remember the previous hardware layout? In which stage the PC is being updated? Among the 5 stages, you know. Comparison is done in the execute stage. Comparison of the content of 2 registers. That is done in the execute stage, but PC updation, that means you had that mux and get, you know, so that this appropriate data path to enable the appropriate data path to update the PC. That portion of hardware is a part of which stage? Anybody has the answer? Yes, no? Huh? In which stage PC is being updated? Hello? Can you hear me?
Sir, could you please repeat the question?
See, there is a branch instruction where you see here, and the next instruction is load.
Yes, sir.
Okay, but the next instruction will be executed if the branch is not taken. And if the branch is taken, then the target instruction will be executed, right? Which is somewhere here, later or earlier, wherever. Now my question is, at which stage you would know that branch outcome and in which stage the PC is being updated with the current with the address of the, depending on the outcome of the branch, PC will be updated, right?
Yes, sir.
So at which stage the PC is being updated among the 5 stages?
Sir, after the execute stage, we know the answer.
You know the answer, but update is done at the end of the memory, in the
Yes,
memory
sir.
stage. See, if you look into the hardware,
Yes, after the memory stage.
after this, right? So therefore, so it will be known only here, at the end of the 4th clock cycle, right?
Yes, sir.
So therefore, so there is a hazard here anyway, because the next instruction will enter into the pipeline here in clock cycle 2, but it would be known here. Whether you are not sure whether this instruction will be executed. It may or may not be executed. It will be executed even only if the branch is not taken. So if the branch is taken, see, here is the, say this is the hardware. So let me show you here. So see this, it is being calculated here. The outcome is known here at the end of the execute, but it is being updated here. See, this is the branch hardware. ALU 0, this enables this, and this being updated here. All right. So this is being updated here. So therefore, if you have to wait until the outcome is known, then at least 3 clock cycles you have to wait. Isn't so?
Yes,
At least 3 clock cycles you have to pay penalty. After that, the branch outcome would be known. So therefore, see, so if you use 3 clock cycles, then possibly, the next instruction can be correctly fetched. And as we know that any hazard can be fixed, because hazard means what? You are waiting for something. So hazards can be fixed by putting stalls anyway. So, but see, you see this for branch, the penalty is very high.
So we keep on executing, and then we sort of, after the branches instruction is executed,
Yeah, that's one possibility. Yes, you keep on executing. You assume that the branch is not taken. Keep on executing, and if something else happens later, then flush. So that's one possibility. But there are nice hardware solutions, like we can resolve this by changing a little in the hardware architecture. We can reduce the penalty to a great extent. So we discuss this in tomorrow's lecture. Okay. It's already almost 1 o'clock. Let us stop here today. Any question? Probably tomorrow would be our last class. I think I'd be able to finish whatever is supposed to be covered in this course. If not, then maybe we'll meet for some time on Thursday, but I think I'll try to finish by tomorrow.